Every time you send a payment, open a crypto wallet, or load a secure website, you are trusting your entire digital identity to a single math problem no computer on Earth can solve. Right now, across millions of miles of fiber optic cables laid beneath the ocean floor, hundreds of trillions of dollars in global value are flowing between banks, cloud servers, and personal devices. Every single second, billions of search queries are processed, private medical records are transferred, and automated stock trading algorithms execute microsecond transactions. Yet, almost all of this data travels across a completely open, untrusted medium. The public internet was never built with physical walls, guarded pipelines, or inherent privacy. Every packet of information you send is broadcast through public routers, switches, and local wireless networks, where anyone positioned along the signal path can intercept and inspect it. So, how does a world built on transparent digital channels prevent immediate financial and political collapse? The answer does not rest on complex passwords, biometrics, or physical steel vaults. It rests on two massive prime numbers, hidden behind a mathematical asymmetry so powerful that it forms the structural bedrock of modern civilization. Without this specific branch of mathematics, modern global commerce would instantly grind to a halt. E-commerce platforms would cease to exist, digital banking would become an impossible liability, and international communication channels would collapse under the weight of endless wiretapping. The invisible mechanism maintaining order across our entire digital infrastructure is known as public key cryptography, and at its core sits an elegant mathematical concept. Multiplying two large numbers together is trivial, but reversing the process is virtually impossible. To understand why our global economy depends on secret prime numbers, we first have to look at the catastrophic flaw of historical cryptography. For thousands of years, secret communication relied entirely on symmetric encryption. In a symmetric system, both the sender and the receiver must share the exact same secret key to encrypt and decrypt a message. Consider the ancient Caesar cipher, or the complex rotors of the Enigma machine used during World War II. In both cases, if Alice wants to send a secret message to Bob, Bob must already possess the exact key used to lock the message. If Bob does not have the key, Alice must physically send it to him. But here lies the fundamental paradox of cybersecurity engineering. How can Alice send the secret key to Bob over an unsecured channel without a spy intercepting it? If they had a completely secured channel to share the key in the first place, they would not need encryption at all. For centuries, this key distribution problem was considered an unsolvable law of physics. If two strangers on opposite sides of the planet wanted to communicate securely without meeting in person, they were out of luck. In the physical world, you cannot hand someone a locked box without also finding a way to give them the key. But in the late 1970s, a team of researchers radically re-engineered our understanding of information theory. Mathematicians Ron Rivest, Adi Shamir, and Leonard Adelhan introduced an unprecedented system that separated the key used to lock a message from the key used to unlock it. This groundbreaking innovation became known as RSA encryption, named after their initials, and it permanently solved the key distribution problem by introducing public key cryptography. In an asymmetric system, everyone gets two distinct keys, a public key that is broadcast to the entire world, and a private key that is kept strictly secret and never shared with anyone. Anyone on Earth can use your public key to encrypt a message meant for you, but only your private key can decrypt it. It is the mathematical equivalent of a padlock that anyone can snap shut, but only you hold the physical key to open. The entire architecture of public key cryptography depends on a special type of mathematical operation called a trapdoor function. In standard computer science, most functions are designed to operate easily in both directions. Addition can be reversed by subtraction, and multiplication can be reversed by division. A trapdoor function, however, is a one-way street. It is a mathematical computation that is extremely easy to perform in one direction, but computationally infeasible to calculate in reverse unless you possess a specific piece of side information known as the trapdoor. A great physical metaphor for a one-way process is mixing paint. If you mix a bucket of yellow paint with a bucket of blue paint, you instantly get green paint. Combining them takes a matter of seconds. But if someone hands you a bucket of green paint and asks you to isolate every single particle of yellow paint back into one container and blue into another, the task becomes practically impossible. In mathematics, the absolute purest form of a trapdoor function is prime factorization. A prime number is a whole number greater than 1 that has no positive divisors other than 1 and itself. Numbers like 3, 7, 13, and 19 are prime. When you multiply two prime numbers together, you get a composite number. If I ask you to multiply 17 by 23, you can do it on a scrap of paper in a few seconds. The answer is 391. That direction of the math is effortless. But if I reverse the question and hand you the composite number 1403 and ask you to discover the exact two prime numbers that were multiplied to create it, your brain immediately slows down. You have to start testing prime factors one by one. The two prime numbers happen to be 23 and 61, but finding them requires trial and error. For small numbers, a standard pocket calculator can find the prime factors instantly, but as the prime numbers grow larger, the time required for a computer to reverse the multiplication grows exponentially. This fundamental mathematical gap between the ease of multiplication and the difficulty of prime factorization is the ultimate trapdoor function protecting humanity's digital secrets.
To truly appreciate how RSA encryption safeguards modern society, we need to look directly at the underlying mathematical steps that bring it to life. The engineering behind generating an RSA key pair is remarkably clean, relying on classical number theory established centuries ago by mathematicians like Leonhard Euler. First, a server or software application generates two extraordinarily large prime numbers, which we call P and Q. In modern systems, these are not small 2-digit or 3-digit numbers. Each prime number is hundreds of digits long, generated randomly by hardware components measuring thermal noise or atmospheric fluctuations to ensure absolute randomness. Next, the computer multiplies P and Q together to calculate a master composite number, designated as n. This number n is called the modulus. Because P and Q are massive, n is a gigantic number, typically 2048 or 4096 bits long, translating to over 600 decimal digits. Once n is calculated, the computer computes Euler's totient function of n, represented as phi of n. For the product of two prime numbers, calculating phi of n is incredibly simple. It is equal to p minus 1 multiplied by q minus 1. This value reveals how many integers up to n share no common factors with n. Here is where the mathematical trapdoor snaps shut. If you know p and q, computing phi of n takes a microsecond, but if you only know n, computing phi of n requires you to first figure out p and q through prime factorization. Armed with phi of n, the system selects a public exponent, usually the number 65,537, because it offers an optimal balance between security and computational efficiency. The pair of numbers consisting of n and the public exponent forms your public key. This public key is published on open servers, attached to SSL certificates, and broadcast openly across the internet. Finally, the system uses modular arithmetic to calculate a matching private exponent called d. The private key d is derived using the extended Euclidean algorithm, satisfying a precise modular equation, where e times d is congruent to 1 modulo phi of n. Once d is calculated, the original prime numbers p and q, along with phi of n, are permanently shredded and purged from RAM. They are never saved on disk and never transmitted anywhere. The public key containing n is public. The private key containing d stays locked in secure hardware. When a user wants to send you an encrypted message, their device converts the data into a large integer m and calculates ciphertext c by raising m to the power of e modulo n. To read the message, your device calculates c to the power of d modulo n. Through the magic of Euler's totient theorem, raising the ciphertext to the power of your private exponent d instantly restores the original message m. Anyone intercepting the message sees only ciphertext c and public number n. Without private exponent d, deciphering the text requires factoring n back into p and q.
To understand why RSA encryption is so secure, we have to look at how classical supercomputers attempt to break it. If a malicious actor intercepts your public key and obtains the modulus n, why can't they simply run a script to factor n back into p and q? The answer comes down to computational complexity and the limits of physical reality. To factor a 2048-bit number using classical computing, you cannot rely on simple trial division. Dividing a 600-digit number by every prime number up to its square root would take longer than the current age of the universe. Instead, computer scientists use the most advanced classical factoring algorithm known to humankind, the General Number Field Sieve, or GNFS. The GNFS algorithm uses complex algebraic number theory to find polynomial relationships that isolate prime factors. Even with the General Number Field Sieve running on the world's fastest supercomputers, distributed across millions of processing cores simultaneously, breaking a single RSA 2048-bit key would require approximately 300 trillion years of continuous computation. To put that in perspective, the universe itself is roughly 13.8 billion years old. The total energy required to power a supercomputer for that long exceeds the combined energy output of our entire sun over its entire lifespan. As long as classical computing laws hold, prime factorization acts as an impenetrable digital vault. It is a mathematical wall so tall that no brute force attack can ever scale it. In real-world cybersecurity engineering, asymmetric cryptography is applied across every layer of our connected lives. One of the most ubiquitous applications is the deployment of SSL certificates securing web traffic. When you type a web address into your browser and see the lock icon next to HTTPS, your device initiates what is known as a TLS handshake. In a matter of milliseconds, the web server presents its SSL certificate, which contains the server's public RSA key signed by a trusted certificate authority. Your browser verifies the mathematical signature on the certificate, confirming that the server is genuine and not an imposter. However, public key cryptography is computationally heavy. Raising massive numbers to multi-digit exponents requires noticeable processing power. Therefore, modern systems use a hybrid encryption model. During the TLS handshake, RSA encryption or elliptic curve Diffie-Hellman is used exclusively to verify identities and securely pass a short temporary secret key between your browser and the server. Once that secret key is safely exchanged, the connection immediately switches to symmetric encryption, such as AES 256-bit, which processes gigabytes of web traffic per second with minimal CPU load. Beyond web browsing, public key cryptography is the core foundation of crypto wallet security and blockchain architecture. When you hold assets in a cryptocurrency network like Bitcoin or Ethereum, you do not actually store coins on your laptop or phone. What you own is a private key stored inside your wallet software. Your public wallet address is derived directly from your public key. When you want to transfer funds, your crypto wallet uses your private key to generate a unique digital signature for that transaction. The entire peer-to-peer network uses your public key to mathematically verify that the signature could only have been generated by the owner of the matching private key, without ever exposing the private key itself. If prime factorization were solved overnight, every crypto wallet on Earth would be unlocked, every SSL certificate would become worthless, and every encrypted database in every bank, military branch, and hospital would be exposed to total manipulation. The global digital economy relies entirely on this mathematical shield staying intact. For decades, mathematicians and engineers operated under the assumption that large prime numbers would protect our digital world forever. But today, our entire cryptographic infrastructure faces an existential crisis known as the quantum computing threat. Classical supercomputers, no matter how powerful, process information using binary bits that exist strictly as zeros or ones. They are bound by the conventional laws of physics, exploring computational paths one by one or in parallel chunks. Quantum computers, however, operate on fundamentally different physics. Using quantum bits or qubits, they leverage the principles of superposition and quantum entanglement. A qubit can exist in a state of 0, 1, or any complex combination of both simultaneously. In 1994, a mathematician named Peter Shor published a theoretical algorithm that shocked the scientific world. Shor's algorithm demonstrated that a sufficiently powerful quantum computer could solve the prime factorization problem in polynomial time. While a classical computer running the general number field sieve takes exponential time to factor a 2048-bit number, a quantum computer running Shor's algorithm converts prime factorization into a quantum period-finding problem. Instead of guessing factors, the quantum computer uses quantum wave interference to evaluate all possible period states simultaneously, collapsing the output to reveal the prime factors p and q in a matter of hours or even minutes. This realization created an urgent vulnerability known as Harvest Now, Decrypt Later. Intelligence agencies and malicious actors around the globe are currently intercepting and storing vast petabytes of encrypted internet traffic, diplomatic communications, and financial records. They cannot read the data today, but they are hoarding it in massive data centers, waiting for the exact day a cryptographically relevant quantum computer becomes operational. Once that hardware exists, they will feed the historic encrypted traffic through Shor's algorithm, instantly stripping away the protection of old RSA encryption keys and exposing decades of global secrets.
We are currently living through one of the largest silent migrations in engineering history. Cybersecurity institutions worldwide, led by agencies like the National Institute of Standards and Technology, are racing to upgrade the global economy to post-quantum cryptography before quantum hardware matures. In mid-2024, NIST released its first official post-quantum cryptographic standards, including FIPS 203, also known as ML-Chem. These new standards completely abandon prime factorization and RSA encryption. Instead, they rely on complex multidimensional geometric structures called mathematical lattices. Lattice-based cryptography poses problems that are computationally impossible for both classical supercomputers and quantum computers running Shor's algorithm. Instead of finding prime factors along a two-dimensional line of numbers, breaking a lattice system requires finding the closest point in a grid containing hundreds of spatial dimensions, a problem that remains intractable regardless of quantum superposition. Replacing the cryptographic engine of the entire global economy is a colossal engineering effort. Every web browser, bank server, embedded IoT device, operating system, and hardware security module on Earth must be updated to support these post-quantum algorithms over the coming decade. The digital world we inhabit feels seamless, instant, and almost magical. But behind every transaction, every encrypted search, and every secure communication, there is no magic. There is only raw engineering, cold logic, and the unbreakable beauty of two secret prime numbers, standing guard over the global economy until the next mathematical frontier takes their place.